What was that, Maureen?
Well, this whole week, ever since we've had that conversation about men not being able to multitask, it's been so evident that it's so true.
Dude, I was
I'll be
such a
talking
big
with my dad, and my
multitasker.
sister will be talking to me, and I have no idea she was even talking to me. And then my mom can like talk to two people at the same time. Like, how do you do this?
I don't know.
I think it's more than you can multitask if something is routine.
Yes. More, yeah.
I can't even multitask.
Conversation for women is more routine.
What?
I could not multitask while watching my TV. Like, I'll be like, I can't
I didn't
like
see
something
you
like,
give it
I'll
to a
stop
year.
and be like,
Well, I'm not putting everyone in a box.
and brushing your teeth was
Because I act like a female.
on routine.
Okay. Yes. Kramer said he's a drag queen.
Kind of.
Kind of.
He's only missing the outfit.
I know you took that way not okay, but
Trinity.
but
I was joking.
I was talking to
I would
Gary
say that your parents have flipped personalities too.
See,
A lot, yeah.
see, I was just talking to that noise.
Not personality.
Not personality, but like.
Maybe I'm
Your dad is very talkative. Your dad is also very sensitive and sentimental, and your mom's not. Same
She
way.
is, she just doesn't express it.
Well, okay, I'm just saying that's not
That's
typically how
my mom's always like,
the traditional gender pour out is, you know?
no, but he's a, like, what is, like,
Most people think I'm like all over talkative, which I'm not. I really don't like to
I
talk.
feel like if you're a teacher, smell is actually smell doesn't tell me what it is. See, you're so
There you go,
weird.
bud. Alright, here we go.
I know it's not so long.
Oh, you might want a pink one, because I do have 3 pink ones if one prefers the pink one. Or if you like multiracial.
Used for an oil spill.
Oh.
I prefer to have
Wait, why does this feel thinner?
big oil.
It doesn't.
Yeah.
that's okay.
Problem.
You are wrong, you're always wrong.
Oh.
Thank you. Thank you. No, it's okay.
Does anybody want a multiracial one?
Multiracial.
Take it.
It's biracial, thank you, please. Thank
Is there a trans race thing now?
you. Trans race?
That way, well, I'm sure there's a trans everything now.
Yeah, I'm in.
Well, I mean, I guess
I've thought about saying I feel like 65 years old today so I can get Social Security.
Your race is your ethnic background. You can't change that.
Oh, well, your
Gender is your
You can't
DNA.
change that.
You can't change that.
Well, I mean,
You see.
Yeah, it's really sad. We have a neighbor.
still, you can't
We
change
have a
where
neighbor
you're
who
from.
has.
How are you gonna change?
We have a
where you're
neighbor who
from?
has a
Are you gonna
brother
change your
who
gender?
is changed.
Well, they still produce the same hormones of the original gender.
Literally, it's starting to look like a female.
What?
Like it's scary. It's really gross.
What did you say?
Our neighbor has a brother
Who's now his
who
sister.
is now
Oh,
like changed. I don't know. I don't even like to use that word.
There was this awkward thing on Facebook that a guy had a crush on a girl who was actually a guy. And I was like, this is crazy.
I saw this.
I read something that
About
a
a
guy
trans
used to be a
trans
girl, fell in
got
love
married,
with
and the guy got
a
pregnant.
girl who used to be a guy. And I'm like, what the heck?
What's
I'm
really,
just confused.
what's really scary is I think they've come to they've come to enough technological advancements that I think that they can reproduce,
Yeah.
which is gross.
I don't think they just grab based yet.
Yeah. Yeah, I've seen articles about it.
Guys having
It's,
babies.
yeah, it's
That's all it is.
disgusting.
Man.
I think they can like insert.
Yeah, there's a lot of
uterus
surgery.
into-
That's so why do you want to do that?
Yeah. It's
a mental
but
illness.
it's a
Honestly,
messed up
I-
and twisted world, right? To those that aren't believers, the cross is foolish. All right.
Well, it's common sense. That's just foolish.
I agree.
I'm so confused.
But quite frankly, guys, I actually had a really interesting conversation with Mr. Weatherly that, quite frankly, life and the world isn't fair. It just isn't. Is it fair that someone's mom commits suicide at a certain age? Is that fair? Is it fair that someone grew up and was only taught how to drink, and so was been alcoholic their whole life. Is that fair? Is it fair that I grew up in a real privileged family that taught me Christianity? I'm thankful, but is it fair? Is it fair that Donald Trump got $23 million in inheritance from his parents, and he thinks that he did something with his life when really he didn't have to hit the ball out of the park, he was already halfway home? Does that make sense?
That made a lot of money.
Yes?
What would happen if a transgender person tried to get in Grandview?
I think that we have a statement that would
Probably shut us down.
not elect them, but let's pray that that never happens, because
I don't think.
That means that
Is it
Grandview would have had to
possible
go
for
so far
Christian
down
to be
that
trans?
things are already happening.
Well,
So
if you don't have
We'll
to
see, I mean,
I'll go Christian school.
honestly,
What if you transgender? And do you give a
I'm just gonna let you guys know,
Christian?
we've had a lot of success here at Grandview over the past 3 or 4 years. And God's doing a lot of good things, but we're on Satan's radar now. You saw something with some of the seriously nasty rumors that started this year. We're a target for Satan. We just are. So, just be ready. Because it's gonna happen. Bad things are gonna happen. Just, you can't expect God to bless without being any opposition. It's a spiritual battle that we're dealing with. Big deal. So, just be aware of that. Alright? Chapter 7. This actually is a very short chapter, only 4 lessons. 4 lessons in a
We're
lab.
taking a test
Next week. Yeah, we're gonna do a molecular shape lab. Yeah, we're gonna work with like the little stick figures.
No.
It's actually pretty fun. I think you'll like that.
I'm so bad at
Okay, so last chapter was really predominantly based around what? What was kind of the main thing we did last chapter? Bonding. We did Lewis structures and stuff like that, right? Okay. So Lewis structures represented molecules that were covalently bonded. However, Lewis structures left out some extremely valuable information. What do you think Lewis structures left out? Okay, sure.
Clarity.
Okay. What else? Orbits, sure.
Orbitals.
Can we do orbitals in 2 dimensions?
No.
So something that really was left out with Lewis structures is the 3-dimensional shape. Okay? Believe it or not, when I do this, that's really not what it looks like. It actually looks more like a hydrogen going into the page, a hydrogen coming out of the page, and hydrogen going like that. Because what that does is completely minimizes the repulsion. The further away you are from each other, the less repulsion you have. And as we're showing this, yes, it's the furthest away these guys can get from each other on a 2-dimensional surface, but it's not the furthest away they can get from each other on a 3-dimensional plane. Does that make sense? Like if you have one coming in, out, up, and down, that's about as far away as you're going to get. Okay? And we're going to talk about those things in this chapter. Talk about shapes, talk about why water acts the way that it acts. Okay? And water is not a linear structure. We'll get into that. Okay, but let's review a few things. If you didn't think chemistry built on itself, wrong. Okay, there are 4 sublevels that we talked about a couple chapters ago. What are the 4 sublevels? S, P, D, F. And the reason why I'm going to review this is because we're going to talk about 3-dimensional shapes, and those 3-dimensional shapes are going to have orbitals. And those orbital shapes are going to come from each sublevel. Each sublevel has a specific shape that these orbitals have. And we'll get into that as we progress. Okay? How many orbitals does S have?
2.
1,
Oh, yeah.
3,
Oh, right.
5,
Yeah.
5, and 7.
Yeah.
Are those your orbitals?
Electrons, 2.
Max electrons. Just coming back a little bit.
6, 10.
Take your orbitals times 2 because each orbital can only have how many electrons in it? 2. Okay. Well, you know, it's all great that we represent a bond with a dash, but it's really not a dash. We know that these are shared electrons here. So how are they being shared? Well, what ends up happening is orbitals from the hydrogen overlap with orbitals from the carbon, and there you have your shared electrons when those orbitals overlap. Well, we gotta know what those orbitals are. We gotta know how they overlap and what they look like and what goes on. So that's what really the point of this chapter is going to be. Okay? All right, valence bond theory. This is one of the theories. This is not all of the theories when it comes to how these guys bond. But this is the one we're going to spend most of our time on because it's the easiest to explain. If you take higher level chemistry classes, you'll see some of the more complicated theories. Okay? So I was just saying that covalently bonded things share electrons when what happens?
Orbitals of different atoms overlap.
When your orbitals from different atoms overlap. Okay? Makes sense, right? See any problems with that? So we're going to talk about sigma and pi bonds. Don't be overly confused or overly scared about the fact that we're using these Greek words and Greek symbols. You'll be all right. Okay? I'll explain bond axis here in a second when I show the visual on the next page. Okay? And the visual on the next page will also help me explain what ends of the orbitals mean, because a sigma bond is when the ends overlap, and a pi bond is when the sides of the orbitals overlap. And I'm going to explain with the visual what an end of an orbital is and what a side of the orbital is. Does that make sense? Okay? Now, if I'm doing something like this, okay? This is always the case. Every single bond is going to be a sigma bond, which means every single bond is the result of ends of orbitals overlapping. So how many sigma bonds do I have up there? 4. Pretty simple? Okay, are we going to have to do Lewis structures probably this chapter? Yeah. Chemistry builds on itself, ain't just going away. Okay? Now, sigma bonds are the strongest type of covalent bond. Okay? Now, if you have a double bond, what you have is a stronger bond than a single bond, but that's because it has both a sigma and a pi bond with it. So the sum of the two is stronger, but sigma is always stronger than pi, which we'll get to that here in a little bit. So let me explain bond axis and some stuff here. Okay? So here's a sigma bond. As you can tell, we're talking about what sublevel?
Yes.
The S sublevel. Okay, I don't know if you guys remember that the S sublevel has a spherical shaped orbital. Do you guys remember what the P sublevel shape is?
It's like a
Dumbbells, right? Okay? So now, there really isn't any ends or sides to the S sublevel, is there? It's all the same, okay? So when we talk about ends and sides, we're really going to refer to the P sublevel, which I'll explain in a sec here. Okay, let's just say this is hydrogen with hydrogen. Okay, do you remember, what's last chapter? The beginning of last chapter when we had that video and we showed the hydrogens coming close to each other and it had the energy, and what happened? The energy did what? Dropped until eventually there was an optimal location where the energy was a what? At its lowest or minimum energy. Okay? That distance we call, they referred to it as the bond length. Okay? Well, on the previous slide it said bond axis. Let me explain what the connection between that is. So bond axis is a region of high electron density that forms a line and connects the two nucleuses. So here's your two nucleuses. Your bond axis would be the axis that goes right between them. Okay? This is also where your shared electrons are going to be in your sigma bond, right? Because here's you see your overlap portion of your two s orbitals there? Everybody see them? So your two electrons are going to be on the bond axis, and it's going to form a pretty dense region of electrons on that bond axis, right in between the nucleuses. Okay, so when we talk about bond axis, it's essentially the line drawn between the two nucleuses where you're going to see a relatively dense electron region because the result of orbitals overlapping and bonding forming. Okay? Did I turn that on? Oh, it'd be really bad if I didn't turn that on. Please tell me I turned that on. Ah, thank you, Jesus. All right? So then what they were referring to was a bond length. The bond length would be the length or the distance between the two nucleuses when they were referring to bond length on that video. Alright, so here we got p orbitals. Okay, now here's where I'm going to refer to sides and ends. Okay? This is an end, this is an end. That is a side, that is a side. Make sense? Okay? So when you have a sigma bond, you have ends overlapping. This would be like fluorine bonded with fluorine, because fluorine's valence electrons, or the ones that it share, are in the what block? The p block. Okay? Hydrogens share electrons in the what block? The s block. So if you had H with F, you would have an s orbital overlapping with a p orbital. But you would still have your region of electron concentration right there. Okay? Question? Anyone? All right. Pi bonds. Pi bonds can only appear after a single bond or a sigma bond. And the previous slide had said that all single bonds are what type of bonds, Gage? Sigma bond. Yeah, I realize. It's just tiring sometimes. Okay? So let's say I'm dealing with this. Okay, I said all single bonds are sigma bonds, but you cannot have a pi bond until you first have a sigma bond. Okay? So with that information, do you think you could tell me how many sigma bonds are up there? There are 3 sigma bonds, and how many pi bonds? 1. Now let me show you what's going on here. Single bond, sigma bond. Single bond, sigma bond. The first bond of a double bond is a what?
Sigma.
Sigma. The second bond of a double bond is a pi bond. Okay? Now, pi bonds are weaker than sigma bonds, but that doesn't mean that a double bond is weaker than a single bond, because it's not the case. Because a double bond has both a sigma and a pi.
Together. Oh, which I got a pi. So,
Okay?
why is it why is it weak?
Because it doesn't overlap in between the nucleuses, which I'll show you. Because the sides of the orbital overlap.
And all the sides.
Yep. Okay, so let me show you. This is kind of difficult to see.
Jesus Christ.
Okay? So here's your nucleuses. This is representing a double bond here. So this would be like this bond right there. Carbon and oxygen are overlapping p orbitals. Okay, here's your bond axis, right? Here is your overlapping what bond? Sigma. On the bond axis, end of end. Now technically there's another portion of this that they didn't write, but they didn't feel like that was necessary. Does that make sense? Okay. Now what do you think this is representing here?
A bond between the two sides.
So technically what they didn't do is they tried to show you how it overlapped without squishing everything so much. Does that make sense?
So
technically these are closer so that this part overlaps with that part. Does everybody see it? Okay? So you'd have those orbitals overlapping there, so your sigma is here, and your pi overlap is above and below. So the reason why it's weaker is because it's not in between the nucleuses, and so it's not quite as strong. It's not held as tightly as if it were smack dab right in between the nucleuses. Does that answer your question? Okay. Now, what about a triple bond?
Oh, that's nice. 1 sigma.
So you should, yep, you should make the connection. Here's your bond, here's your nucleus, your bond axis is here. Does everybody see the sigma bond? On the bond axis, overlapping. Now they tried to do their best they could to show 3 dimensions here. Okay? Now if I can see this, this would overlap with that, and same with that. And this would overlap there, and overlap there.
Christ.
You'd have to push it together to actually get them to overlap. They're trying to show you that without completely making the bond here look goofy. It's a molecular sandwich, pretty much. Okay? So, this would be an example of this. How many sigma bonds are here?
Why?
4,
4.
2.
2.
And then
I've heard 1, 3, 4, and 2. What is it?
2 sigma bonds.
2 sigma
Two
bonds.
pi bonds.
2 sigma bonds and how many pi?
2.
How do you know that?
Okay? Every single bond is a sigma. So there's a sigma bond. And the first bond of either a double or a triple will always be a sigma.
Is there another type of bond besides sigma?
No, so
okay,
the
got it.
first one is a sigma and the other 2 are pi.
Okay.
Make sense?
Yeah.
So let's see if I can come up with any other examples. How many sigma, how many pi? 2 sigma, 2 pi. Now, for Mr. Kramer, there isn't any single bonds there. Well, all sigma bonds are single bonds. Also, the first bond of a double or a triple is always a sigma. Make sense?
Yeah.
Okay.
Ooh, it's a spider.
So this is kind of showing you that every double bond will always be 1 sigma, 1 pi. Every triple bond will be 1 sigma and 2 pi, which is what I've already showed you with these Lewis structures. Okay? Now, if pi bonds are weaker than sigma bonds, why is a double bond stronger than a single bond?
Because it has more.
It has.
They're more tightly held together.
It has more, what do you mean more?
Well, it has more bonds.
Connected.
It includes a sigma as well as a pi.
Yeah. A single bond is just 1 sigma bond. A double bond has a sigma which equally matches a single bond, but also has a what?
Pi bond.
A pi bond. Okay, so yes, pi bonds are weaker than sigma bonds, but double bonds have both. That makes sense?
When they're together, they're strong.
Yes, when they're together, they're stronger. Triple bonds are going to be the strongest because you still have that sigma, but you also have the 2 pi's now. Make sense? Questions? Oh, we got you right in the head, too. Those days, man. What'd you do? What'd you party all last night or what?
Just think about it, Kylie.
I was thinking about.